Hello, everyone. This is Yan Zhang, the instructor of this course, CSE 2020. From this video, we will start the Module 8, Set and Map Abstract Data Types and their implementations. That means the Module 8 will cover two abstract data types, set and map. Now we will start from set abstract data type. In this video, we will focus on set abstract data type and its implementation. The learning objectives of this topic is to define set abstract data type, design and implement set abstract data type, and apply set class template defined in the STL standard template library. Okay. The set abstract data type. A set is a container that stores a collection of unique elements following a specific order. So we say a set stores a collection of sorted unique items. There's no duplicate in the set. The values of an element identify the element itself, and each element value must be unique. We don't have duplicates in a set. And the element values cannot be modified, but they can be inserted or removed from the set. So we cannot modify the element in a set, but we can remove element from the set and insert new element in the set. And then the set, the elements are always sorted in the set. So the elements are always sorted following a specific ordering criteria indicated by its internal comparable objects. So that means that all the elements stored in a set are comparable. So we can sort them from the smallest to the largest. And we can store a collection of integers in a set because we can compare integers. And we can store a collection of strings in a set, and we can compare strings. And we also can store a collection of employee objects in a set if we overload the greater than and less than operator for employee objects. So we can compare two employee objects. That means the employee objects, they are comparable. We can store them in a set. Okay, now these are operations of sets. First one is empty. This operation returns true if the set is empty. Otherwise, is empty, return false. This is an accessor. And then the next operation is get size. Get size returns the number of elements in the set. This is an accessor. Return type is int. And then we have the find, this operation. Find x. This operation returns true if element x is in the set. X is a parameter. And next one is insert x. This operation inserts element x to the set. And then remove x. This operation removes element x from the set. So these two, they're mutators. And then the last one is make empty. This operation makes the set to empty state. That means this operation removes all elements in the set. We get an empty set. Okay, these three operations, find, insert, and remove, these three operations are very important. We will analyze the time complexity of these three operations. Okay. Now here we define the set collection of elements, or the collection of sorted unique elements. And we also define the operations of set. And now we will see how can we implement set abstract data type. So we need to store a collection of elements. Here we can use array or linked structure to store this collection of elements. And set also requires the sorted element. The elements are sorted in the set, so we use sorted array to implement set, and we also can use a sorted linked structure to implement set. Sorted array means elements in the array are sorted from the smallest to the largest. And similarly, the sorted linked structure means the elements in the linked structure are sorted. And we also can use a binary search tree to implement set. Okay, now we will take a look at these three implementations and compare the time complexity of find, insert, and remove these three operations based on different implementations. Now, in this video, we will talk about these two using sorted array and sorted linked structure to implement set abstract data type. Okay, first one, use a sorted array to implement set abstract data type. Here we use a dynamic array. Use dynamic array to store a collection of elements, or I will say the unique sorted elements. And we also have another two attributes, size and capacity. So the array, this has a fixed capacity. So we need this capacity attribute. And now this is a sorted array. So that means for example, we have elements in this array 10, 20, 30, 40, and the 50, and then the 100. The elements in the array are sorted. And now the operation find x. For the operation find x, we can use a binary search to implement find x operation. Binary search means we will find the middle element, compare the middle element and x. If x is less than the middle element, and then the next step, we search x in the first half of array. So if the x is greater than the middle element, we will search x from the second half, or we say the right half of the array. This is the binary search, and the binary search time complexity is big O log n. We talk about in the module 3, algorithm analysis. So we know the binary search time complexity is big O log n. So that means the find X use a binary search time complexity is big O log n. And then the next operation is insert X. Insert a new element in this sorted array. So after we insert X, after we insert the new element, the array still sorted. So now that means we cannot just insert X at the end of the array. We need to find the right position for X in the array and then insert X. Okay, we find the right position for X in the array. Now, if the X is in the array, now we find the right position for X in the array. If X is in the array, we do nothing. We don't insert duplicate in the array. So if X is in the array, we do nothing. We don't insert X in this array. If X is not in the array, we insert X at the right place of array. Okay, now assuming we want to insert element 45. So we use a binary search to find the right position of X in this array. Okay, now we use a binary search. We say now this element, the index, for example, the index I, if the 45, we insert 45 in this array, its right position is index I. And now at the index I, we have this element 50. So now we need to do is we need to shift all the elements from index I to size -1. We need to shift all these elements from index I to size -1. Shift them to right. Shift them to right by 1 cell. So that means we move the 100 to left, and then move this element to left, etc., and move the 50 to left. Now the index I, this position is available. Okay, we move the 50. We move the 50 to I plus 1 index. Now this position is available. We insert 45 here. So we need to shift the elements from the index I to size -1. We need to shift all these elements. Now the worst case is what? The worst case is we need to add the element at the index 0. So we need to shift n elements in this array, shift all the n elements to right by 1 cell. The worst case is big O(n). We shift n elements to right by 1 cell. So shift part is big O(n). And the binary search big O(n). So now for the insert operation, the time complexity is a big O(n). Find the right position for X and the shift element, put X in the right position. So we add this together, we have the big O(n) time complexity. So insert X is a linear time complexity, big O(n). And then for the remove, now the remove X, remove element X, here we have the, we need to find the X in the array. Okay, I will remove this. to remove element X, we need to find X in the array. If X is not in the array, we do nothing. Else, we remove X from the array. If we find X in the array, we remove X from the array. Okay, the first step, find X in the array, we use binary search. Binary search, the time complexity is big O log n. So this is the find X in the array, big O log n. And then we remove X from the array. This is the big O n. So I still use this example. We want to remove 45. We want to remove the element 45 in this array. So remove means we will use a 50 to override 45, and then use a 60 to override 50, and then we use 100 to override 90. So that means we need to shift the elements from index I plus 1 to size minus 1. We need to shift all these elements to left by one cell. This is how we remove the element 45. So if the element 45 its index is I, we shift elements from index I plus 1 to size minus 1. We shift all these elements to left by one cell. The worst case is we need to shift n elements. We need to shift all the elements in this array. It's big O n. So the worst case is a big O log n plus big O n. We remove the lower order term. So we have the big O log n, linear time complexity. Okay, this is these three operations when we use a sorted array to implement set abstract data type. Now we also can use sorted linked structure to implement set abstract data type. So here we have a pointer, head is a pointer pointed to the front node, and the size is a attribute, private attribute, to store the number of elements in the set. And for the operation find X, this linked structure does not support binary search. So we have to use linear search to search element X from this linked structure. Example is we have the head pointed to the front node, and then we have this node, and they're connected by the pointers. Okay, this is the last one. We have this 10, 20, 30, 40, 50, and the last one is 100. Now to find an element in the linked structure, we have to start from the front node, from the head, and then compare X with the element. Not match, we move to next one. So we have to use linear search. Linear search, the time complexity is big O n. This is the big O n, linear time complexity. And then the insert element X in the linked structure. So for insert, after we insert X, this linked structure should be still sorted. So we need to find the right position for X in the linked structure and then insert X. So if X is in the linked structure, we do nothing. We don't insert duplicate in the linked structure. And if X is not in this linked structure, we insert X at the right position. So now find the right position for X is big O N, linear search. And then insert X at the right position is big O1. Because this linked structure, we don't have to shift all the elements to left or right. Now assuming we want to insert 35. Now we see we use the pointer pointed to the node. It's a smaller than 35. And then we just create a new node, and then the new node next pointed to the previous next, and the previous next equal to new node 35. So now in the linked structure, we add a new node. This time complexity is constant time complexity, big O1. No shift n elements, no need to shift n elements. So we have the find X, find the right position for X, and insert X, big O(n) plus big O1, and we still get big O(n), linear time complexity. And then remove element X. We find X in the linked structure. If X is not in the linked structure, we do nothing. We want to remove element X, but X is not in the linked structure, so we cannot remove it. We do nothing. If we find the X in the linked structure, and then we remove X from the linked structure. So in fact, we remove the node contain element X from the linked structure. So here find the X, we use linear search. Linear search means we start from the head, from the front node, and then move to next, until we find the matched element in the linked structure. Linear search, big O(n). And then remove X from the linked structure. It's a big O1, constant time. And then big O(n) plus big O1, we still get linear time complexity. So that means we use sorted array to implement the set, and this is the linked structure to implement set. And for the find operation, the array is what? Array is big O log n. Big O log n. And linked structure is big O(n). Because the sorted array, we can use binary search, but for the linked structure, we have to use linear search. And then for the insert X, the sorted array implementation is big O(n). Linked structure is big O(n). And then for the remove X, the sorted array implementation is big O(n). Linked structure is also big O(n). So far, if we compare these two implementations, the sorted array implementation is better than linked structure, because the find operation, this is a big O log n, better than big O(n), and the other two, they're same. Okay, this is the two implementations. We also can use binary search tree to implement the set abstract data type, but we will talk about this in the separate video.